So we'll start with any questions from that. Anybody got anything? Victoria? 7 or 8? Sure. Okay. So let's do 8 since you have the answer to 7. So it'll be more helpful if we see 8 and then you can do 7 and check it. You know what I mean? Sound good to you? All right. All right. So if I'm doing k of x, I'm interested in this part of the data table. Right? I guess use the same color. So what I'm going to do is I'm being asked to write an exponential function. So I want something in terms of a times b to, or y equals a times b to the x. Or I guess k of x. So I'm going to start by creating a system of 2 equations using the information in my table. So basically this is like each row is like an xy. So I have 16/9 equals a times b to the second. And then my other equation is 13/27 equals a times b to the third. And that's like my system. So I'll call those equations A and B. Victoria, good so far? To solve this system, I'm going to use elimination. To decide which one, or to do the elimination here, since the variables are being multiplied, I have to divide the 2 equations. So the question becomes, which one do I want to make the numerator of my division problem? Which one do I want to make the denominator? Typically, I pick the one with the bigger exponent to be the numerator. So I'm going to do equation B divided by equation A. So far, so good, Victoria? Okay. Let's simplify the fraction here on the left. So to divide 2 fractions, we're going to take the numerator and multiply by the reciprocal of the denominator. So 9 goes into 27 3 times. 16 goes into 32 2 times. And on the right-hand side, the A's reduce and the B's reduce, leaving me with just a B to the first. Is that okay? Well, like the A's just reduce, right? I have 3 B's on. 32. Well, 16 goes into 32 twice. So that just reduces, leaving me at 2 in the numerator. Right? And then 9 goes into 27 3 times, so it leaves me just a 3 in the denominator. So I have here that B is equal to 2/3. Cool. From that, I can plug that into one of our 2 equations. I'm going to pick to use equation A. And now I'm just going to solve for A. So 2 times, or 2/3 squared becomes 4/9. And then I'll just multiply both sides by 9/4 to get the A by itself. So the 9's reduce, 4 goes into 16 4 times. So there's my value for A. So I think this was K of X is what we called this, is 4 times 2/3 to the X. Does that feel okay, Victoria? Yeah, no problem. And again, like if you're doing this, you could do like 5 and 6 the same way if you wanted to, although it's not as difficult to do it, or there's an easier way to do it since we have the x coordinate that's 0. So that allows us to do a shortcut for ones like 5 and 6, which are really no different than, or could be done the same way as 7 or 8, but there's also a faster way to do it if you prefer to do it a faster way, which is what I would prefer to do, because I'm all about saving time. Jake? Well, this just tells me the a. The x coordinate is 0, tells me the y is coordinate there is a. And once I have that, I can take any point I want. I would do this one. So I would say that like 4 is equal to 12 times b to the first. And if I solve for b, I just get b is 1/3. And then I just put it back together. Is that cool? So again, that was massively easier than what we just did because we had this, the point where the x coordinate is 0. Gives us a automatically, and then there's no system to solve. Much easier problem. As opposed to 7 and 8 where we don't know the x coordinate, or we don't know a point where the x coordinate is 0. That's why we had to solve the system there. Is that cool? Yes, Claire? Well, I mean, I just did 8. It's like the exact same problem, and the answer is in the back of the book. So, like, I did, you know what I mean? Yeah. Like, I'd like you to try it, and then we can come back and we can do it next time, if that feels okay? Yeah. Okay. You get my reasoning, though, right? Yeah. This is an important problem for you to try because I have a feeling it'll probably end up showing up on the test. So I do want you to have a chance to try one, rather than just me doing both of them and end up, you know, some people just copy both the work down from what I did and just not really do it. It's like, I kind of want you to do it. You know what I mean? But I'm happy to do it again at a later date. But since I just did 8 and it's like the same problem, and 7's the one with the answer, I figure it's a good one to wait on. You know what I mean? Okay. Anybody else? Cool. Well, let's pick up where we left off. And we'll finish up section 15.1 today, because remember we had already started this last week. Or no, Monday? Did we start on Monday? Yeah. Boy, it felt like last week, didn't it? This was a long week. All right. So on Monday, we talked about how we have these exponential functions, a times b to the x, where the a is non-zero, the b is positive, and the b is not equal to 1. Right? You guys remember that? So these exponential functions all can have different bases, right? Which makes it kind of difficult to compare two exponential functions to one another, to be like, oh, which one is going to be like growing faster, and like how much faster might this one be growing than another one, or whatever. And it just kind of makes it inconvenient if I want to try to compare two exponential functions. So what we're going to want to do today is we're going to want to find a different form for these exponential functions where the base is always going to be the same number. So the question becomes which number to use. And the number we've decided on is this one. We call it the natural base, or Euler's number, credited to the mathematician Leonard Euler. He's on the Hall of Fame there on the back wall there somewhere on the far right. We denote that number with the letter E. Those of you that remember your Algebra 2 from last year, that should look familiar. The definition for E, it's the limit as x approaches infinity of 1 plus 1 over x to the x. So how would have we figured this out? Well, one way we could have done this is to just kind of do it computationally. So what I've done here in the first column is just like a bunch of values. So I have like all the way out to like 500 something, and then I have another one here at like 10,000 or something. And these are just going to be my values for x. So what I'm going to do is 1 plus 1 over, and then my first column, to the first column. Press enter. And then I can just evaluate this for each of these values of x. So like if I put 6 in for x, I get this number 252. So I'm going to go ahead and do this all the way. Look at how awesome a computer is, right? We did all those computations just like in the blink of an eye. But what we're noticing here with the pattern is that as these values of x keep getting bigger and bigger and bigger, the difference between the y values keeps getting smaller and smaller and smaller. And eventually, as x gets big enough, it just kind of settles down to one specific number. So the approximation for this number is, let me make sure I copy it down right. So it's about this number 2718, yada, yada, yada. This is an irrational number. So what does it mean when a number is irrational? Does that mean it does things that make no logical sense? Or it acts out of emotion rather than thinking about what it's about to do? No, Mr. Kulik, that's like the English language version of irrational. When we say something's irrational in math class, though, what are we saying? Or when a number is irrational? What does that mean? When it what? When it can't be a ratio, which is the same thing as a fraction. So this is a number that cannot be written as a fraction. So if we were to look at a number like that, what we'd be looking for is something that never ends, so it doesn't terminate. For example, 0.25 is not irrational because that fraction ends. That's 1/4. And there's no pattern to the digits. So like 0.3 repeating is a rational number. That's just 1/3 because there's a pattern to the decimal. It's just 3s over and over and over again. Everybody's okay with that? Here, there's no pattern to the decimal, even if it looks like there's a lot of 2/8 and stuff you're seeing there. Everybody's okay? Cool. So, what this allows us to do is give us another way to represent an exponential function. So another way we can write an exponential function is a times e to the kx, where a and k are non-zero. So any function we can write as a times b to the x. We could also write as a times e to the kx. We'll talk about how to do that transformation back and forth between those a little bit later. Is that okay? All right, so when we talk about exponential functions then, whether we're talking about either version, there are basically two types of exponential functions. So if a is positive, and if the b value is greater than 1, or the k value is greater than 0, we call this one exponential growth. And if the a value is positive, and either that b value is between 0 and 1, or the k value is negative, we call that exponential decay. And then if the a value is negative, in the first case, that would make it a decay. And if the a value is negative in the second case, that would make it growth. You guys get what I'm saying there with how I wrote that? I just don't want to copy it all over again. So in red, it would say, like, if a is less than 0 and either b is greater than 1 or k is greater than 0, then that's exponential decay. Right? That I kind of read it like. You get what I'm saying? The way I wrote that? I just don't want it to be confusing and not have to write it another million sentences. You know what I mean? Okay. All right. Let's do an example here. And this example is like a story problem or whatever. So rather than me writing all the words, I'm just going to copy and paste it from the lesson and just drop it in here. Is that cool with you guys? Don't worry, I'll make this bigger. All right. Given the population of a certain city is in 1999 or 1990, jeepers creepers, speak, is 782,248 people, and the population of the same city is in 2000, 895,193 people. And assuming the population growth is exponential, in what year will the population reach 1 million people? So the way I'm reading this is it sounds like every 1 year they do like a census and count the number of people or whatever. Everybody's okay with that? So we're told that the population is exponential. So I would say, okay, I'm going to use a model like this, where the population is like my dependent variable, and like the year is my independent variable. Everybody feel okay with that? Since it certainly seems like the population of the city is going to depend on the year, that makes more logical sense than thinking the year is going to depend on the population of the city, right? You guys buy that? Okay. So here's the trick that I'm going to employ to make this a little bit easier. The earliest date that we know anything about is 1990. I'm going to just make that time 0 then. Why is that going to be convenient for me? Think back to what we talked about when we looked at number 6 from the previous lesson. If the x-coordinate is 0, the y-coordinate is the value for A. So by choosing to represent 1990, the first year we know anything about, as time 0, what does that force my value for A to be? Yeah. Is everybody okay with that? You like this trick, right? This makes life tremendously more convenient to do that. Now, you could leave it as 1990, but then you're going to end up having to solve a system of 2 equations like we did before, which is kind of a hassle. You know what I mean? Mr. Kulik would prefer not to have to deal with that. So if 1990 is time 0, what is 2000? Times time 10, right? Everybody good with that? So using this then, we can say that P of t is equal to 782,248 times b to the t. And if I want to solve for b, I'm going to plug in 895,193 into my P of t. And I'm going to plug 10 in for t. Claire, what's up?
I was just wondering, like, what 2000 was. Does 2000 go into the equation?
So 2000's a date.
Or, like, is that, like, how many? Like, I can't see what's written above it.
T equals 10.
Oh, okay, so.
If 1990 was T0,
then, okay.
10 years later is 2000, so the T would be 10 for 2000. Does that make sense?
Yeah.
Okay. So I'm here, right? We're solving for B. What do I need to do next to get B by itself? Okay, is the 782,000 being added to B? It's being multiplied. So to move it to the other side, I have to divide. Okay. So now we have a b to the 10th on the right-hand side. How do I change that to just a b? We did this last year. Inverse? I mean, no, not really. I mean, that's too broad of a term. Like, sure, but what's the inverse of the 10th power? What if it was b squared? What would we do? Square root it. So what are we going to do for b to the 10th? So we're going to 10th root it. Yup. So remember the way we wrote that is we just put the 10 like inside the check mark part of our radical. Now because this is an even root, it needs to be a plus or minus when we're doing it to both sides. If it was an odd root, do I need the plus or minus? Nope. Remember with even roots, can we take the even root of a negative number? No. Can we take the odd root of a negative number? Yes. And if you think about it, for example, if you multiply 3 negatives together, you get a negative. So it's okay to take the odd roots of a negative. If you multiply an odd number of negatives together, it's still negative. So an odd root of a negative is fine. It'll just be a negative number. No big deal. Okay. So that'll get the b by itself. Now remember, b. What are some of the restrictions on b when we talk about an exponential? One of them is that it has to be greater than 0. So if I go back to this plus or minus, do I really need the plus or minus there? No, man, because the b can't be negative. So it's just going to be the positive. And now it's going to be calculator time. All right. Who remembers how to type a 10th root into their calculator? All right. So I'm going to do a 10, and I'm going to press math, and I'm going to scroll down till I find the x square root option here, and that'll get me a 10th root, and then I'll just use the fraction command to type this fraction in, just so it looks exactly the same as it does on my calculator. Okay. So there's one way of doing it. Alternatively, if you remember from last time, we talked about square roots being the same as an exponent of a 1/2. You guys remember doing that? So a 10th root is the same thing as the exponent 1/10. So I could also do this same problem this way, where I do exponent to the 1/10, and gives me the exact same number doing it that way. Either way is fine, whatever way you prefer. Whether you want to use the radical command or the exponent command, either is fine. Okay? Everybody cool with how to type that kind of thing into your calculator if you need to use a big root? All right. So we have this. We're not done, though. So now where are we at? So this is our function. Everybody's cool with how we came up with that? But the question asked us more than just that. It then says, what year will the population reach 1 million people? What year will the population reach 1 million people? Oops. I'm calling that T. So what year is it asking us to solve for T or P of T? What year will the population reach 1 million people? What year? What year? T, right? Remember, where did we put in the, when we did the T equals 10,000, where did we put that? or t equals 10, right? That went in for t. So we're solving for t. Then what are we going to plug in for p of t? Yeah, the population at that year, which in our case is 1 million. Okay. So if we want to solve this algebraically, does anybody remember what we have to use to do this? Where's our variable located? In the exponent. Who remembers algebraically what operation do we have to use to get that out of there? That's right, Claire, say it loud. A logarithm. Have we talked about logs yet this chapter? Nope. So do you think we're going to use a log right now to do this? Nope. Instead, we're going to just do this on our calculator. Okay? So to do this on our calculator, we will talk about logs, just not yet. But I wanted to acknowledge the fact that, yes, we've done enough in our prior classes to do this algebraically, but we're not ready to do that, review that quite yet. So what I'm going to do is I'm just going to type the left-hand side into y1. So I think that's 1 million. That's 6 zeros, isn't it? Looks like it. And I'm going to type the right-hand side into y2. Everybody's okay with what I just typed in? Now, if I just hit zoom standard, I'm going to see a fat lot of nothing. So I'm going to reset my window, and I'm going to do this kind of intelligently. So I'm going to think about the context of the problem. Remember, the x's are representing our times. So in this problem, our time is starting at 0, right? That's the first date we know about. So I think x min being 0 is appropriate. And then at time 0, the population is 782,000. At time 10, the population is 895,000. So it went up about 100,000 people or so. If we want to get to 1 million, how much longer do you think this is going to have to go? Probably at least another 10 years, right? So probably at least time 20. I'm going to do 25 just to be sure. I like to overestimate. Everybody's cool with that? There's no penalty in overestimating when we're trying to do a problem like this. You'd be better off overestimating than underestimating. And then we'll go up by 5s. Now the y-coordinates are representing the population. What's the smallest population we're concerned with? Well, like that 782,000, right? So I'm going to pick something slightly less than that that's a round number. So I'll do like 750. The biggest value we're concerned with is 1 million. So I'll pick something maybe a little bit bigger than that. How about like 1 1/4? And then going up by 100,000 seems appropriate there. So let's hit the graph. So here's our line at 1 million. Here's our population curve coming in. And where's the solution to this equation going to lie? At the intersection. Very good. Those of you that have to take an ACT in the near future, this is an effective solving technique. If you don't know how to solve the equation, it's like algebraically, I don't know how to do this. You just type the right-hand side and left-hand side in your calculator and find the intersection. Does the window matter? The window only matters so that you can see the intersection. As long as you can see the intersection, it's fine. Everybody's good with that? All right. So how do I find the intersection with the calculator? Second trace, very good. And the command I'm looking for is intersect. Shocking. The intersect command requires 3 inputs. It asks for what 2 curves are we trying to find the intersection of, and then give me some place that's a guess. Now, how many things did we have in our graph here? We just had 2 things, right? How many times are they going to those 2 things intersecting? Just once. So all I'm going to do is press enter 3 times because the calculator will handle everything else. There's only 2 things to look at, and there's only 1 intersection. So just, I'm not even going to read the things. I'm just going to press enter 3 times real fast. And it tells me that intersection is at 18.21-ish and a million. Okay, so how would I answer the question? So Jay's saying that we just add 1990 to that and we call it 2018 then. So when I do the census in 2018, the population will be at least a million? No, why not? Because it turns a million like a quarter of the way through 2018. Really, we want to say at 2019 would be the first year that the population is over a million. Jack. Yes. How's that feel? That's okay? Now, if I took this same function and I said, okay, well, what happens like 100 years later? Or 200 years later? What's the population of the city going to be? So that's 11 million. Does that seem reasonable that the city population has gone from 700,000 or 800,000 to 11 million in the future? That's kind of tough to buy, right? Like, who's to say there's even going to be a city there? Like, isn't the city like a finite size? Can it really just grow forever like this? Probably not. That's not a very realistic scenario, right? There's only so much land that people could settle in. And yes, you could build up, but you can't build size skyscrapers everywhere because you just need like too much water and power and police and all these other things. And just like the traffic's a nightmare, and just like nobody's going to want to, are there enough jobs to support 11 million people? And it goes on and on and on and on with reasons why that might not really be feasible. So when we're describing populations like this, usually there's kind of like an upper bound of what's a reasonable population, what's a lower bound for what's a reasonable population based on like the carrying capacity, right? Even in the wild, like if there's, like no predators, like the prey are not going to just grow and grow and grow and grow and grow forever. They'll grow until like they've eaten all the resources in an area, and the population crashes because they all starve to death, right? There's like an upper bound for how much population you could get. So what we're going to do here is we're going to design a new function that's going to have like a built-in upper and lower bound to it, but still kind of grows exponentially in between. So this is going to be called a logistic function. So let's say we have A, B, C, and K. These are all positive, and that B value is greater than 1. Less than 1. We say a logistic, that's the type of function we're talking about, growth function, is of the form f of x equals c over 1 plus a times b to the x, or if you prefer your exponential written in the other form, 1 plus a times e to the negative kx. And if the k is negative, or the b is between, or if the b is greater than 1, then this is a decay. All right. Now, one of the key features for these logistic growth functions is that we have horizontal asymptotes at y equals 0 and y equals c. So if we think about the graph for this, we'd have like a horizontal asymptote here at 0. We have another horizontal asymptote here at c. So like our growth function would look like this, where from left to right it's increasing. And our decay function would look something like this, where from left to right it's decreasing. Okay, so let's look at a specific one of these logistic functions, and let's talk about some of the information we can say about it. All right, first things first. This is a logistic function, correct? We can see that because we have that exponential part in the denominator. It fits the form. Is this growth or decay? Is this logistic growth or decay? This is logistic growth. And the way that I remember this is if I look at the exponential piece, this is exponential decay. But since it's in the denominator of the logistic function, it like flips to growth, right? It just inverts it. You know what I mean? Okay. And maybe let's be specific here. Claire. Yeah. So exponential decay, you're looking at the value for b, and for exponential decay, that value of b has to be between 0 and 1, and for exponential growth, it would have to be greater than 1. Now, for a logistic growth, it basically just means you have an exponential decay in the denominator, which is what we have here. For logistic decay, it's you have an exponential growth in the denominator. Is that cool? Okay. What are the asymptotes at here? All logistic functions have a horizontal asymptote at 0, and then again at c. What's the c in this equation? The numerator, which is 10. Everybody's cool with that? Okay. What's the y-intercept going to be? What's the x-coordinate of a y-intercept? Think about the picture. So like a y-intercept is here. 0. So if I plug 0 in for x, what's 0.6 to the 0? 1. So I have 3 times 1 down there, which is just 3. So 1 plus 3 is the denominator. Agreed? So I have 10 over 4. And yes, you could reduce that to 5 over 2. That would be preferable. Or the decimal 2.5 is also appropriate. Does that feel okay? And just for grins, let's take a look at this function so you can see the dueling asymptotes here. Okay, and I'm going to reset my window here, but the standard window should be appropriate here since I know everything is between 10 and 0. So there's my picture. And again, I'm going to turn the axes off so you can really see that horizontal asymptote at 0. Oh. I was like, that's not the picture I want. I forgot to put my multiplication symbol there. There we go. It's like, there we go. So this is my logistic growth curve, right? So this is the horizontal axis. This is y equals 10. I'll put the axes back on so you can really kind of see. So again, following the y equals 0 and then following up here at y equals 10. Is that cool? Okay. And let's do one more story problem example and we'll be done here for today. Sound good to you guys? Yeah, I thought you might be cool with that. Okay. So basically we're recasting this previous problem, this time using a logistic growth model. So it says the population of a city can be modeled using the logistic growth equation, where P is the population of the city, T years after 1950. At the beginning of what year will the population have 1 million people? So basically all I'm doing is plugging 0 in for P of T. Everybody's okay here? And I can tell this is logistic growth because if I look at the exponential in the denominator here, since the k value is negative in the exponent, I know this is exponential decay. Which would imply then that this is logistic growth, right? Claire, is that cool? Okay. Just wanted to re-hit this since it was a question earlier. Okay. But all we're really doing is we're typing this stuff into the calculator and looking at a graph, right? Everybody's cool with that? All right, let's do it. So one input is the 1 million, the left-hand side. The other input, I'm going to type in exactly as it looks. So I'm going to use the fraction command. Do you remember how to get the E on your calculator? To get the E to show up, we press second and the LN button, which is here on the left-hand side of your calculator. That'll give you the E with the exponent on it. Second LN. The LN is on the left-hand side of your calculator, just a little bit up from the on button. Did you find it?
Oh, yeah.
Okay. All right. Again, we're going to reset the window here. Here for the time, if we're assuming 1950 is time 0, and we're going, I don't know, how long is this going to take? No idea. I'm going to guess 100 years because, well, I'd rather overestimate than underestimate. You know what I mean? I'm given no indication about the starting population, so who knows? We can always come back and make it wider, but 100 years is probably appropriate. The Y minimum should be 0 because I know that this is a logistic function, so the one horizontal asymptote is at Y equals 0. The Y max should be the other horizontal asymptote, which is at $1,425,397, the value for C. Now, I'm not going to type all those numbers. I'm just going to do it 1.5 million because that was like a lot of numbers to have to worry about. And then going up by 100,000 seems appropriate. Let's hit graph. There's my 1 million line. Here's my logistic growth curve. I'm interested in the intersection. If I had graphed this and I couldn't see the intersection, what would I want to do? Yeah, just expand the window by picking a bigger value for x. You know, I might do 150 or something next if I didn't see it. But we do. Second trace, intersect command, enter, enter, enter. 79, basically even, right? That's basically 79 even. So that would be, when I add 1950 to it, that would be the year 2029. Notice I didn't have to worry about rounding up here since this was like 79 even, right? And this feels like a good place to stop. At this point, you guys should be able to do up through 16 on this problem set. Okay, notice that the 9 through 16 isn't appearing in Sunday's problem set, but next Sunday, so you don't have to worry about it for this weekend. This will be a pretty short problem set, but that seems reasonable considering you had to have a test this week also, so you probably did a lot of work getting ready for that already. Any questions for me about any of this? Okay. Worth giving you guys a heads up. Those of you that are